Hello and welcome to Moxa's webinar, Best Practices for Hazardous HMI Design, Bringing Control Where It Hasn't Been Before. I'm Martin McHugh, and I'll be your moderator today. If you have any questions at any time during the webinar, please use the questions pane by simply typing in your question and clicking send. At the end of the presentation, we will do a Q&A session and take as many questions as we have time for. We will follow up with any unanswered questions after the webinar. All right, let's get started. So we'll have 30 to 40 minutes of presentation with 15 to 20 minutes of Q&A. Today's presenter is Tom Knuth. Tom is the Vertical Marketing Manager for Moxa's global oil and gas businesses. He has worked in the industrial computing and networking industry for his entire career, with targeted efforts in coordinating industrial networking technologies within process automation with enterprise capabilities such as high bandwidth switching, data acquisition, and remote asset management. With that, I'll hand it over to Tom.
Thanks, Marty, and thank you to everyone that's joined. I hope that this is informative and fluid enough for you guys that we keep you coming back. We want to cover it. The title is, of course, HMI panel design. I know that's some confusion. We want to use that term slightly interchangeably today to just basically draw down the distinction between a simple HMI and what is typically regarded as a panel PC. Okay, now as we move into the agenda, actually we're having a slight delay here. Bear with us for one moment okay, great. Looks like we have a slight lag time here. We wanted to simplify it to the why intelligent HMIs are being developed and deployed in the field, how robust panel design technology is bringing intelligence to the field, and what defines best practice in HMI panel design and actually hardware manufacturing practice for industrial networks, specifically within oil and gas. Before we get started, though, it makes a lot of sense and it brings a lot of value to us to understand who's listening, and it helps us form our webinars here in the future. So if you guys could take some time and identify yourselves, we can better form our webinars and this webinar, as a matter of fact, as we proceed. So just take a few moments and we'll move on. Well, as we move forward into the challenges of what define the challenges in hazardous areas in HMI applications, specifically within oil and gas, I'm sorry, we're having a slight issue here. Okay, great. We just had the poll results in. A lot of the people on the call probably are familiar with the oil and gas industry. Margins are growing incredibly thin. Oil extraction points are moving into the Arctic Circle, for a very long time in the desert plains. It's not a place conducive for high technology, especially HMI or panel PCs for that matter. Additionally, he said margins are growing thin, and the 10-year trends towards safety and innovation continually push, I guess you could say, a sprint towards efficiency and increasing margin lines. Now, as we evaluate those challenges, the first is quite obvious, and that's temperature. The problem: these crystals in conventional HMI screens and panel PCs freeze with low temperatures and destroy the image and actual panel display completely. And in hot zones, as we see all the time, and actually the central USA and Saudi Arabia, we're going to have a fusion of the panel screen. We have both displays here actually tested at the Moxa facility. But you see, as we continue on, and related to the heat issue, sunlight and screen displays are also an issue to consider when choosing an HMI or a panel PC for that matter. We're going to discuss it in terms of nits, which is candelas per square meter, and the SI unit is a defined unit of luminance. Most screens and HMIs that you're going to see are going to be somewhere between the 3,000 to 7,000 nits. For an industrial PC or an HMI, you're going to want that to be over 7,000 nits, simply because the insulation of the screen is going to knock that down a bit, and of course it has to be bright enough to resist the sun. I'm sure all of us can analogize this to our phone. If you're trying to actually read your phone screen, for example, your iPhone in the middle of the summer's day, it's nearly impossible to read, and for that matter, it gets extremely hot extremely quick. So that on the previous slide we saw above 50 degrees Celsius, that's nothing in terms when we look at an average summer's day in Saudi Arabia, and that temperature below negative 20 degrees Celsius is nothing as well. This one's titled Onsite Serviceability. I know that's that's something that's a term that is always a challenge in oil and gas. We have two images here, I think, that kind of summarize exactly why that's an issue. But in some sense, an interchangeable title could be remote access. We have rigs that are extremely remote. Putting personnel out there is not only expensive, but it's dangerous. When you have a HMI that can essentially, growing more advanced, and I guess you could call it a panel PC, if you can place it out there in the field and have one or two operators control the assets in the field, what once took a whole team of people, that's much more effective. It's a lot lower in cost, and if it's a powerful PC for that matter, it's a lot better for your bottom line. But as all technology does, it does break down, or prior to it breaking down, it requires being serviced. So there's a lot of features that we'll identify here as we proceed in the presentation that really provide added value and safety for when you're choosing an industrial HMI and panel PC. Because I know that if you're operating in the field and you see this, it's a bit of an issue. You can't call the tech guy in your office. It's enterprise technology in the industrial realm, and there's no enterprise solution, so there's no tech guy. So we're going to talk about what we can do to avoid this. Now that we're getting off to a little bit more fluid start, let's go into the second poll here. Where are you guys seeing use of panel computers as HMIs in the oil and gas realm? Please, we'll have 4 choices here for you to choose from. I really wanted to identify HMIs and panel PCs interchangeably in this presentation, just because we're seeing the fusion of them continue as technology increases. We're just going to pause here for a moment while we get all your guys' answers in. All right. Thank you guys for participating in that. Now we can get into the technology quite a bit more. It looks like most of you guys are identifying it as the control room, which is something that we expected to see. But we do see mobile fracking operations quite a bit, which is something that we hoped to see. We had somewhat of a pulse on that market, and I think that really illustrates what we're talking about here. And that's the reason why we're using HMI and panel PCs interchangeably here. It's just simply because the fact of mobile computing is really bringing HMIs into the level of computing here. So moving into that, we're going to go directly into the best practices to address those challenges of the market. Dealing with the cold temperature issue is something that's commonly addressed within heat, which we will also address later. But cold is a separate issue, specifically within industrial HMIs and PCs, simply because heating a unit is much more complicated than cooling a unit, especially for a unit that has a screen, an LCD at that. LCD is liquid crystal display, so that freezes. Liquid freezes, as we all know, and once it hits 0 degrees Fahrenheit, 20 degrees Celsius, I'm sorry, reverse that. You're going to see the whiteout, as I showed in the earlier slide. That's not something that you can simply turn a heating mechanism internal into the PC or HMI to fix. It needs to be addressed specifically to the LCD screen itself. So in order to address that, when you're choosing an HMI or panel PC, you want to make sure that the internal components of the computing unit can operate at negative 40 degrees Celsius. That means before the screen even turns on, the computer is essentially working. You're just not seeing the screen turn on. You also need to have an internal mechanism that can sense temperature, and the reason that is that we want to have a heating profile, an intelligent heating profile. So when we reach a certain low temperature, that heater turns on, addresses directly to the LCD screen, not necessarily the internal unit. And once it reaches a certain height of temperature, it can shut off. And so you see this graph here at the bottom. It's adaptive, it's dynamic. It's not just turning on the heater and then turning off. That's really important for an HMI that has to be placed in, say, a drilling rig in Alberta, Canada, or Alaska for that matter. And a way to address that too is just from a simple design feature is that it generally should have 2 heaters inside so that the heat dissipation can be evenly dispersed in the unit. This is maybe a benefit to some or a confusion to others. I personally like to shy away from these types of graphs, but for the engineers out in the field, this is a great flow path of how the intelligent heating system works. It's basically from power on to temperature recognition to heat to appropriate temperature being reached or recirculating to more heat. And you can see you can follow the pathway all the way through to overheating protection. But this is pretty much how IHS works. This is how the heating profile manages itself internally in the unit. This is something that you want to have in any industrial unit that has to be placed in any place that can get cold and actually hot for that matter. Here's an example of the simple, and it sounds quite complex when we're describing it, but this is the way it looks if you take the heating sensor out of the unit and look at it. It's attached to the main motherboard, which is a design feature that will lead us into another benefit that you probably, and actually attribute that you really want to look for in an industrial panel PC or HMI, and that is less parts the better. A minimalist design is better. Having it attached to the unit, yeah, it might increase, say the sensor breaks down, it might increase the cost of replacement, but in general it won't, because the cost of sending somebody out there to open up the system, do some diagnostics, you're losing production time, you may not even find the problem, and it's a lot of man hours. You know, I thought I would really just show how the sensor works and show how it's attached, because say it goes down, you can just replace the whole unit, be done in a matter of minutes rather than hours. Now heating is probably something that you guys are probably more accustomed to dealing with all the time, especially in the Middle East and even central USA. It's something that's dealt with quite commonly with a lot of industrial manufacturers of switches and some PCs, but I wanted to cover it a little bit more in depth and break it down, maybe a little bit more specific, of maximizing cooling efficiency. It's kind of an art form in some sense. You see these robust housing structures for these complete self-standing HMIs or panel PCs that don't have to be embedded in a I guess you would say a dashboard or control dashboard. They look like they're just built to endure rain and abrasion and things of that nature, but actually it's more intelligent than that. You see those fanless designs in the back, those metal fans in the back. They're vertical for a reason, and the width of the metal is the certain width for a reason, and the placement of the internal components are there for a reason, and it has to do with heat dissipation, convection in other words. So here's a heat map, ultraviolet heat map for a temperature simulation of our unit. A lot of competing units will have something like this as well, and you'll notice that the heat dissipation is quite even across the entire back of the panel. That's something that's extremely important. You'll see some competitors claim that they're industrial grade, but the heat dissipation will be red in certain sectors of the back of the plane, which is a recipe for overheating and short lifespan of the unit. And the reason why it's so even is not only the internal construction, but those vertical fans that I mentioned earlier control airflow, and for whatever reason our testing has shown that that vertical fan design is much more effective than lateral. And you see the thermal temperature graph on top. And as I mentioned earlier, the actual placement of the computing units, whether it be the CPU or processor or motherboard and fuses inside need to be evenly placed and well thought out as well. So it's it's just as much as a technologist's view as a hardware construction as well, hardware engineering considerations as well. You want them evenly placed to work with the unit, not work against it. And you know, if we open up our PC, it looks somewhat like this. You can see there's minimal parts, and the computing units that generate heat are evenly placed apart from one another, as to not overheat a unit in a specific area. Now, we mentioned sunlight on the screen. This is a little bit more of a breakdown of all the layers that go into a touch screen in an LCD panel. It's not just obviously the glass and the LED bars that give you the picture. There's a lot of insulation and conductive material between that protective glass and the LED bar display. And this is kind of showing it from a side view of what it actually looks like. The reason I really wanted to bring this up is with a resistive versus capacitive touch screen, there's a lot of things to consider in an industrial HMI. Generally, we're going to have to shy away from capacitive, something that's similar to your iPhone or iPad, and go towards resistive, which uses some electromagnetic forces of the human body, but mainly it's force controlled. So you place your finger, for example, on one place on the screen. It takes a command and say, for example, it's a button, it's an operation. You click on off. You push that with your index finger, it goes on and off. It doesn't matter if you have a glove on or if you have your bare hand. It will function, it will operate. Additionally, though, looks like we have a slight delay on the screen. I'm trying to go to the next slide to you guys. Bear with us here. There we go. Back and forth, back and forth. When we're talking about the candela, or I guess you could say the brightness of the LCD screen, this is a breakdown of why having a high nits count, which is the candela per square meter, is important. Because as you saw that breakdown at that side view, that cross-section of the screen, there's a lot of insulation that is required to put an LCD screen out in, say, an oil and gas environment, whether it be freezing cold temperatures or extremely hot temperatures. It has to resist heat, it has to reduce cold, and of course it has to reduce fluids, chemicals, and abrasion. With that said, there's a loss of clarity in the screen. It's less bright, it's less clear. So for any industrial HMI, it's counterintuitive, but it has to have high clarity and it has to be extremely bright, something that you would expect somebody at, I guess you would say, a Best Buy store trying to sell you a gaming PC. You would expect them to say, but it's actually really important for the industrial realm as well, simply because there's so much that goes into a screen that can resist an industrial environment that it needs to be bright enough and clear enough to shine through. So generally, we recommend over 7,000 nits for any panel PC that has a strong requirement of visibility for the operator to control operations. You're going to want that, because when it's all said and done, you're going to lose about 1,000 to 1,200 nits just by having a robust screen and insulation layer under that screen for your panel PC or HMI. You have to see a display here. And I touched on this intermittently. Actually, we're waiting for the next slide to come up. Here we go. I touched on it earlier about having an even dispersion of heat-producing units within the unit to affect the ability for us to have even heat dissipation, but it's also important for serviceability. So if we have everything combined into one motherboard, say a backplane, a screen, and then we have the internal units, the guts of the computer, if you will, it's three pieces when it's all said and done. So say after 10 years, we have, we're doing remote diagnostics on the computer. We realize that the risk for it failing are extremely high in the next 6 months, and that we need to replace the central processing unit or 2 of the heaters, it might be more cost effective and quicker just to order an entire central piece and switch it out. Then you can just open up the PC with a few screws and replace the entire computing unit in the middle. Now that we've kind of gone over some of the design principles, we'd like to ask your guys' perspective for dealing with customers or actually being operators yourself. From your perspective, what's the biggest challenge in remote HMI and panel PC control systems? Is it temperature, costs, serviceability, remote diagnostics, or software? Or is it certifications for that PC? I'll wait a minute for you guys to get your answers in, and I'll read them to you guys live. Thank you guys for your participation in this. This is great live feedback for us. All right, the results came in. Even amount of people identified cost and temperature as being a huge issue. The second most identified concern is serviceability. The least is remote diagnostics. The most is certifications. That's great. We always identify a must for at least for these panel PCs or HMIs to be at least IP66 qualified and Class 1 Div 2 certified. So I'm glad you guys brought that up. That's something we should have covered actually earlier in greater detail. But yes, we hear you loud and clear on that. We're moving on to the next slide here. Just a slight lag time for you guys. All right, looks like we've moved on. Now, trends of preventive maintenance and self-recovery is one other thing we want to go over before we start narrowing down this presentation towards the end. Now, you guys did identify remote diagnostics as a lesser concern, but you did identify temperature, cost, and serviceability as issues of high concern as well. And we're going to kind of tie in why remote diagnostics actually are important for those 3 other reasons. Number one, they ensure oil field assets are operating properly, and with that said, by the same measure, they can ensure that the computing unit's operating properly. So we can have in-time decision optimization for your oil production, but we can also have in-time diagnostics for the computer PC. So if we see something, if we have any temperature irregularities or any concerns of operations, it's going to give you guys a remote report of that computing unit in the field and letting you know it's ready for replacement, or the screen's too hot, or something of this nature. That's really important for ensuring that your people in the field actually have an operation that works and that they have visibility to their assets. We're going to touch upon this here a little bit earlier. Now, you want to have an embedded SNP system in the computing unit that allows for those remote diagnostics to feed back to, say, a central control room. And as I mentioned, that's not only important for you guys to have access to what that HMI is controlling in the field, whether it's a oil platform drilling station or it's a drilling rig. That information is going to be fed back in real time to the SCADA or control room. It's also going to feed back the information of the actual PC itself. So in some sense, that panel PC becomes part of your mining asset. You're part of your drilling or overall operation asset pool, not just the communication method for control in the field. I'll go to the next slide here. We're having another slight delay. Here we go, PC health indicators. Now, that embedded SMMP functionality within each panel PC or HMI is going to give you a report on CPU usage alerts, temperature alerts, memory usage, voltage abnormalities, and storage drive alerts. So if you're running low on memory and the threshold's being reached, it's going to give you a value of capacity, and you guys can address that in real time. And Lastly, we're going to have smart recovery and smart recovery options. So say the catastrophe happens and your PC goes down in the field and you don't know what to do. Well, any I guess you could say high quality industrial HMI or panel PC will have a internal log or memory log that if it's shut down for any reason, it's rebooted up, the assets it's coordinated to control in the field and the memory and data logs within that computer are going to be time series backed up to a set date and time. So you could have an auto log every 4 hours for every day, and it fails an hour after that, then you're just all the assets it's controlling it and you have visibility to, and the control rights will still remain intact, assuming that you didn't change something within 30 minutes of the shutdown. Data won't be damaged. System garbage will be omitted, and system damage, it will be able to, it will either be completely recovered or fixed, or at least the information will be able to be extracted and the unit replaced with limited downtime. So in summary, we wanted to really distill what we believe are the 6 main points for an intelligent HMI or industrialized panel PC that should be considered and should be necessary for anything that you're putting in the industrial realm, especially oil and gas. And that is that it needs to have a sealed construction. It needs to be impervious to obviously sand, liquid, and abrasion. Preferably IP66, as I mentioned earlier, and Class 1 Div 2. That goes without saying. Intelligent heat dissipation. IHS, that it looks like it's actually there twice, actually slightly different. High LED nits rating, above 700 nits, minimalist construction and fanless design, and remote diagnostics and auto boot functions in case of the forbidden or foreboding breakdown of a computer. You don't lose any of your data and you don't lose control of your assets in the field. And I also want to draw another distinction about those two heating principles. Heating dissipation is slightly different than intelligent heating solutions, in that heat dissipation has to do with the physical construction of the unit and how it actually disperses heat from a convection standpoint. And IHS is going to deal with the heating mechanism for cold. So that brings us to our end. I'd like to open it up for questions and start a dialogue with the audience. With that, I'll give it to Marty to facilitate the questions.
Great, thanks, Tom. Yeah, we're now going to open it up for questions, so feel free to type a question in your chat pane or your questions pane, and we'll have Tom answer those accordingly. Looks like we have one here. The first one, Tom, is from Chris, and he's asking, what's the difference between simple heating and intelligent heating solution? And more specifically, he wants to know what exactly is IHS.
I guess it's because I stuttered a little bit there on the end between intelligent heating dissipation and IHS, and it's a bit confusing, I know. It's a fancy acronym for IHS. It's essentially a fancy acronym that just describes the temperature mechanism within the unit, not just turning on the heater once it really drops to a certain temperature and then turning off once it reaches a certain temperature. It needs to be adaptive. It needs to have a constant sensor on the outside temperature and heat accordingly. So say it drops to, it turns on at -5 degrees Celsius at a certain level, but once it drops to say -20 degrees Celsius, it's to a new level. It's heating at a faster pace at a hotter temperature. So that's one aspect of IHS. It's tiered, it's adaptive, it goes with the environment. It does not just turn on and off. And the second part of IHS is that the heat will be focused on the LCD screen, the panel itself. A lot of times, as I mentioned earlier, the computing unit should turn on with no problem at -40 degrees Celsius. It's extremely cold. The screen won't work at that point. So with that said, we need to have a different heating attention placed on the actual LCD display versus the computing unit. An intelligent heating solution will do that as well. It will heat the crystals, not necessarily the computing unit at all times. Intelligent heating dissipation, that has to do with the even design of heat-producing units within the computing unit along the inside of the panel PC or HMI, and the actual construction of the metal housing and fans that most effectively dissipate heat and increase the pace of convection. So increase the pace so that thing can cool off. That's it.
Great, thanks, Tom. This next question is from Marc. Marc is asking, what type of associated apparatus in the unclassified location is needed to interface to the HMI in the hazardous location? All right, one more time. What type of associated apparatus is, what type of associated apparatus in the unclassified location is needed to interface to the HMI in the hazardous location?
Well, it's a complex question. The associated location or the associated apparatus is a bit confusing. You can tether an HMI, or in this case an intelligent HMI or panel PC, to a lot of operations. So it all depends on the operator's use of the panel PC. They could be controlling, a drilling rig, for example, land-based drilling rig. It's going to have to. It can be inserted into a dashboard of sorts, so it can be regarded as an embedded system. And in that case, the full unit being IP66 regulated might not even be a necessity. It could only be applicable to the actual front pane and screen. So that's one answer for that scenario. If it's self-standing and it's out in the desert, for example, and it's functioning almost as a mini control room, it's not just an HMI. It's actually, a control center of sorts, and it's controlling it's on an oil platform. The associated apparatuses for that matter will, obviously depend on the regulations that are required for an offshore operation. You'll probably have to have NAB or DNV certifications that have to be marine grade. The entire unit will have to be IP66 minimally, Class 1 Div 2, and everything attached to it will have to fall under that categorization as well. So wires will have to be, busing or whatever, however it's attached to the operation, need to be insulated properly. If you would like, I would encourage you to, write that question a little bit more detailed, and we can get you guys actual specific answer. If you guys have an operation in mind, we can definitely address that.
Great, thanks, Tom. This next question is from Don. He's asking, why a resistive touchscreen and not a capacitive?
Okay, that's a good question. Resistive touchscreen, the biggest design feature is single touch, and capacitive is multi-touch. So your iPad or your iPhone is multi-touch. You can do things with multiple fingers. 2 fingers registers a different command than one. Simply put, resistive is simple. It's more simplistic. It's less advanced. It's oftentimes less desirable, but it's required a lot of times in industrial networks because people wearing gloves, for example, or if they're not, it's a dirty environment. It's a rough environment. You can't use a capacitive touchscreen. Simply put, for that reason. Not to mention that capacitive requires a strong connection with the electromagnetic pulse of a human body, so your fingers. So, even if you're using a bare hand and say you sweat or there's water on the screen, it's going to interfere with that. It's not going to be. You're not going to have a strong command to the HMI. That's changing. We're actually having the ability to have multi-touch functions with resistive screens. So the functionality that you like, say, with a dry hand on your iPhone or your iPad, will be possible in the future with resistive touch screens. But that's the reason why is people in the industrial realm have to wear gloves, and there's a lot of things, whether it be sand, water, or extreme cold temperatures or gloves, that require resistive versus capacitive touchscreens.
Great, thank you, Tom. This next one comes from a different Marc, but there's a few questions here. So Marc's got a couple things. Let me go through it for you, and then hopefully you can respond. Is the thermal management tied in the processor to read T-junction and other areas of the enclosure? And then also, as a follow-up, if so, is there a balance created that determines what the determining temperature is? And then another follow-up question, what happens if the unit overheats? So let me know if you need me to go through that again, and I will, but feel free to go ahead and answer all those questions.
Marc, I love you and hate you at the same time. Those are great questions, but also complex ones. Is the thermal management tied to the processor to read the T-junction and other areas of the enclosure? Let me follow up on the T-junction, but I will say that it is tethered to just about everywhere that the temperature meter can touch. So it will be influenced to temperatures touching the housing of the unit. It will be reading temperatures influenced and coming from actual heat-producing processors within the unit or the motherboard, and it will be sensing, obviously, as I mentioned, temperatures from the LCD screen as well. So the simplistic answer to your question is yes, it's tied to other areas of the HMI and enclosure, HMI and panel PC enclosure. Is it 100% effective on every square centimeter of that unit? Probably not. I'll have to follow up with you on the T-junction part of it. And what happens if the unit overheats? That's a complex question. We like to say it won't, at least on any temperature recorded on the planet Earth. But if it does, it does have a overheating mechanism where it will shut the computer off, at which point you guys can capitalize on a auto boot function once it reaches a temperature amicable and safe enough to operate without damage to the computer. That's what the auto boot function's for. But that's, that question speaks to the importance of having a computer that has an insulated LCD screen and can operate well over 50 degrees Celsius.
Great, thanks, Tom. Next question is from Juan. I will paraphrase the question, but the question's asked: how many temperature sensors are in the main board, and also are there temperature sensors outside the cabinet of the panel PC HMI?
Well, in the example we gave, there was 2. But you saw that it was also in wire form in some sense. So it spans a considerable length of the internal operation of the PC, and also there are temperature measures on the screen. So in some sense you could argue there's 3 that cover a great deal of area on the unit. Relative to, this is a general best practice for HMI, so this is not coming from Moxa specifically. Generally, it's stated that a HMI or panel PC that's operating within the field and claims to be industrial and ideal for high heat, high or extreme temperature operations, it might be advisable to have temperature meters installed in, say, the housing unit that this might exist in, of course, but that's not a package deal per se. That it would all depend on the user's requirement. Obviously, that would add costs to the manufacturer where it might not be necessary. So I hope that answers your question.
Great, thanks, man. We also have another one. This one is from Rob. Rob wants to know: are resistive touchscreens far more or not as susceptible to damage in an industrial environment?
Yeah, that's a good question. The answer is yes. They're less resistive. The reason for that is that they can have a higher capacity for insulation. They're tougher. The insulation actually is the reason why they are more robust and more resistant to abrasion. When you have a capacitive touchscreen, it's you think of your once again, I'm using this ad nauseum, but your tablet or your smartphone, yeah, it will be hard. It'll be essentially glass right in the beginning. There will be no insulation or soft touch that will actually give into any, say, granule sand or a corner of any hard object. So that screen can break. It can scratch with sand, etc., and it also won't read correctly if there's water on that screen, for example. So yeah, resistive will be much more robust. It will be much less, I guess you could say, much more resistive to abrasion than a capacitive touchscreen. Long answer, short answer. With a short answer.
All right, we have another one here from Juan. Juan lets us know he's got temperatures near 42 degrees Celsius. Is it possible to use this HMI in those types of conditions? He also states, obviously adding radiation and convection heat. Just wants to know if it's possible. And a follow-up would be, how many times would they expect the HMI to work? I guess what is the expected life of that HMI? And I'm assuming in those types of conditions.
Yeah, it should operate with no problem there. The tests we ran were over 50 degrees Celsius, so that's pretty much our best practice number. I can answer for Moxa's HMI and say that they will operate reliably slightly above that temperature grade, but that's the line in the sand that we drew, and so that's well over your operation temperature. Should not be an issue. And what was the second half of the question?
The expected life of the HMI.
Well, that would all depend on the manufacturer. I know that Moxa has stated warranty and lifelines to the products that they produce, but that would all depend on the embedded system you're trying to, embedded or self-standing system you're trying to place in the field. I will say that, for example, I can only speak for Moxa in this standpoint that we'll state a warranty and operating temperature, and it should be completely standard in your facility because your operating environment is under the max operating temperature that we test for. So,
great, thank you for that, Tom. Looks like we do have another question from Rob. Rob would like to know, how do you manage solar loading resulting in surface temperatures of up to 140 degrees Fahrenheit on the screen? Any insight there, Tom?
I would say that we would try to avoid it at all costs. That would fry the computer. I hate to say it. You wouldn't want to put. Essentially, you would want to organize your operation that would not be in that direct heat wave. You could put it behind a solar unit or things to this nature, but it would have to be in housing that would manage that temperature flux. Personally, I don't know even of unmanaged industrialized switches that could endure a long lifetime in such a high heat.
Okay, great. The next one, actually, Marc has a follow-up to Juan's question. So, Marc, again, with regards to Juan's question about 42 degrees C operating ambient temperature, does Moxa warranty the increased heat load from the solar impact of the HMI being installed in direct sunlight?
That's a warranty issue, and I could get myself into trouble likely answering that. Just to play the safe card there, but I will say that if it's under 42 degrees operating temperature, there shouldn't be no problem. And I will also say that these PCs were manufactured to operate in direct sunlight. So with that said, it would be something to definitely take up with that I can actually look into further for you, but I think it would probably be a best scenario to evaluate your actual installation.
Okay, thank you, Tom. This next one comes from Chris. Chris asks, what are the most important parameters, features for Class 1 Div 2 environments? I'm assuming of the features of the HMI.
Okay, if I understand the question right, generally it has to be impervious or not necessarily waterproof, but it needs to be extremely water resistant to general fluids. It needs to meet a certain be impervious to a certain heat parameter, which actually we exceed. Yeah, that's pretty much it. It needs to be resistant to chemicals, lip fluids, loose to dust and abrasion, and it has to adhere to a certain temperature away from hot and cold.
All right, thank you, Tom. Rob also wants to know if our units should not be operated in direct sunlight. I guess a clarification on a previous question.
Oh, no, these panels are constructed to be operable in direct sunlight. That's one of the things that we actually call out as a definitive design feature and functionality that any industrialized panel or HMI should have, and that being it should have the high temperature grade, at least up to 50 degrees Celsius, which is more or less 140 degrees Fahrenheit, or even higher than that, I believe. It should have an insulated screen, and with that insulated screen, not only is it resistant to temperature, but with the high nit, the high brightness of the LED crystal display, it should be able to be operable and clear within direct sunlight.
All right, thank you, Tom. I'll give a few more seconds, or give you guys for those last questions that you want to type in, and let those come in for a little bit. But it looks like we got another one here from Rob. In the Middle East, irrespective of ambient temperature, solar loading will result in surface temperature far higher than ambient. Well, thank you for the insight, Rob. Let me know if there's a question in regards to that, and Tom can follow up with you directly. All right, we have another one from Marc. Marc asks, what is the time to boot and have the LCD visible at negative 40 degrees Celsius?
The time to boot, well, that's actually a good question. We probably in our test logs, and I can't answer that immediately. I will say that, say if it will boot, the computing unit will boot immediately at negative 40 degrees Celsius. It's at that temperature, the intelligent heating solution or system, the dual heaters within the core and LCD screen will heat at full pace. I'd imagine it'd be under a few minutes.
Thanks again, Tom. Another question here from Chris. Chris wants to know, what are the most important features for explosive gases, natural gas environments?
Well, most of it's going to have to do with being internally sealed. So essentially anything that can create a fire, intrinsically safe is the buzzword here. Any electrical communication within the unit shall not and cannot be able to ignite any external gas. So it needs to be tight as a drum. That's important that is as important or more important for oil and gas networks as it is from the other way around. So of course, as manufacturers, we're worried about sealing the unit so it lasts long, and it does not go down due to penetration of oil, sand, or things of this nature. But it's probably even more important for fracking operations or any oil and gas operation near a lot of natural gas that any electrical current in the computer doesn't spark anything. So yeah, that's integrated into the design feature of our PCs. I know that for a fact. And that's why it's rated Class 1 Div 2, and that's why it's IP66. That's the answer.
All right, thank you, Tom. We have another follow-up from Rob. He wants further clarification on intrinsically safe. So are we saying that the unit is intrinsically safe? Are there any other methods of protection that we are using? So just follow up with Rob real quick.
Yeah, Rob, would definitely like to send you the specs on the certs that are available for our core panel PC and HMI construction. We also have an embedded unit that does customized solutions. So the options are quite expansive. It would really just depend on what your operation is, how much you're willing to spend, and what you're looking to accomplish. You know, if it's essentially buildable out there, we can accomplish it on our end. But the core products will all be IP66 and Class 1 Div 2.
Great. Thanks, Tom. With that, we're going to go ahead and conclude the webinar. Thank you again, Tom, and thank you to everyone for your interest and participation. Just so all you know, each of you will be receiving a follow-up email with both the webinar recording and presentation slide deck. Lastly, please take a minute before logging off to fill out our survey, as we really value your input and feedback. Thanks again for tuning in, and have a great rest of the week, everyone. Bye-bye.